All right, everybody. Well, test 4 o'clock. The clock on the wall isn't working, but we can use the one from the computer to stay on schedule a little bit. I hope that you guys are doing well and enjoying this springtime weather when you can between all the studying. And I know it's a busy time of year too, but busy for all of us, myself included. Um, just want to get you oriented a little bit as to what you need to be thinking about as of now. There is a homework assignment due tonight. It is homework 21 on section 8.3. And if you have any questions on tonight's homework, so far there's one problem on the board over here, which I'm going to solve in a little while. If you want to add any others to that list during our break today, you can do that as well. But anyway, this is the homework on annihilators that we learned about last week. So this is due tonight. And then I just want to give you a heads up, the next homework, which will be due on Tuesday, which is number 22. This one involves the variation of parameters technique that I went over with you on Tuesday and the stuff we're going to do today. So that next homework is actually kind of a longer one. We've had a couple of shorter ones with these last couple of assignments, but this next one's a little longer. I would not wait until Tuesday to start homework 22 because there's 3 different sections that it's going to be involving. The good news is we're only going up to 24 on homeworks, so we're really getting close to the end here, and just a couple more assignments after these 2. So anyway, I will have office hours after my second class tonight, so if you want to jump into Zoom or come in person, 8 p.m. until midnight with about an hour off at 9 o'clock to go grab something to eat. But besides that, I should be around. In terms of when I'll be around over this weekend, I will send you an email. I'm not quite sure. I usually try to go hiking one day of the weekend, and I just don't know when that's going to be yet. But once I have that figured out, then I'll send you some office hours over the weekend as well. Probably Monday would be a good bet for sure, with the homework being due on Tuesday. So that's coming up. And then just a little further down the road is our next midterm. So it's not next Tuesday, but the week after that. So I am pretty sure I've already published a resources folder, and it's just like the previous ones. There are 2 sample midterms in there. And I would recommend that everybody try at least one of them. And if you have time and if you feel you need to, maybe try them both, maybe with a little bit of space between them to do some studying. There's also a review packet that kind of just overviews everything and gives you a checklist of the things that you should be able to do. And then I probably need to still update exactly what my office hours will be for the exam. So I'll have some extra hours, obviously, leading up to the midterm here. And then there's also a review session with a handful of questions that I went through, and then there's a video that goes with that. All of that stuff is, as always, optional, and it's kind of up to you where you're feeling, how you're doing. You know, if you think you're on top of everything, maybe you don't need to do all that stuff. But if you feel like you have the time and you could really use the help, there's plenty of stuff there for you to look at. So it will cover, just to kind of get this into your heads now, it will cover chapters 6, 7, 8, and 9. We have so far made it up through 6, 7, and 8. So these next 3 lectures, which would be today, as well as next week on Tuesday and Thursday, I will be talking about chapter 9. And you can see that I've roughly broken down the exam to be a quarter of the exam on each of those chapters. I do want to warn everybody that chapter 6 was covered before spring break. So we had a big gap there. It was a while ago. So you will want to, probably most of you are going to want to maybe go back to that a little bit and remember what we were doing there. The chapter 8 stuff is very fresh. We just covered this chapter 8, so that's good news. And some of the stuff in chapter 7 is going to get brought back up to the surface this week and next week as we talk about chapter 9. There's quite a bit of an interplay between those 2 chapters. So I really think chapter 6 is the one that can get lost, since we happened to cover it like right before spring break. So, but anyway, so that's kind of the breakdown. And like I said, the resources folder is in Canvas, ready to go. If anybody wants to start working on it early this weekend, you're, more power to you. Have at it. Okay, so it's just up there for you to optionally take advantage of. Does anybody have any questions about any of that, James?
How would you say people have fared with this upcoming test to the first two tests?
Oh, that's hard to say. That's really hard to say. I would say that the material is a little less abstract than what we had on the second exam, but maybe a little more abstract than the first one. So it's somewhere in between. But there's also I think sometimes the end of the semester, people are just, all your classes are kind of reaching a tipping point, and it's like there's a lot of stress. So sometimes that can work against people too. So I guess all I can say from that is try to get some sleep, get some rest, pace yourself with this. We've been going for 13 weeks already, and so I can understand by the third midterm and the end of the semester, it may not even be so much about the content as just about sort of how you're feeling about, oh my God, I've been going since January without a break kind of thing. So just have to kind of pace yourself. But yeah, I would say that it's another one of those things that each individual student has to assess. There's some students who do great with this very computational stuff. They're really happy with the differential equations, and the linear algebra is the part they don't like. But there's also students the other way around that really eat up the theoretical side of the material, and they struggle a little bit more on the computational stuff. So it's really hard for me to make any really clear, broad, sweeping statements. Yeah, so. And I haven't even thought about the test yet, so I don't even know what I'm going to be asking you, but it'll be that material, that's for sure. Okay, so without further ado, any other questions for now? Guys, today is the day. We are going to start the last chapter of the book that we're going to actually cover in this class, which is chapter 9. And I'm going to skip over the first section of chapter 9 after I do a quick little intro, and we're going to jump straight into 9.2. This is where we're going to put it all together, right? You will see almost everything we've learned for the first 13 weeks getting recycled again, or coming back up into at least something relevant to what we're going to be doing here. So in chapter 9, let me give you a quick look. The reason there's no recap up here is we're just kind of starting fresh here on this new chapter. This is about linear systems of differential equations. So we're going to spend the first half of our class today introducing this idea, and then the second half of the class we're going to do the homework questions, and I've got a group work for you, and we'll practice a little bit of this stuff. Okay, so we've studied linear systems of equations before, but we have not studied linear systems of differential equations, right? So this is where we're kind of merging together differential equations with systems of equations, right? And just to get this motivated a little bit, I guess I can call this motivation. I'm not going to dwell too much on this. The book does have some examples of this that are actually concrete. Do you guys remember way back to the start of the semester when I had a tank of chemicals and there was some kind of a solution here with an amount of chemical at any time t? And there was, there was some kind of an inflow, a faucet that was turned on, and there was like some kind of a rate of inflow, which was R1, and there was a concentration of chemicals pouring in, which was C1. And then there was actually a leak in the bottom of this flask or whatever that had a outflow rate of, say, R2, and then a concentration flowing out of C2. You remember this problem? And the unknown function was A of t, and there was a differential equation for it, right? So in this problem that we did it in chapter 1. It was a linear first order differential equation. So we had an application of that material right away at the beginning of the semester. But in this problem, there is one unknown function and one tank or flask or beaker or whatever it is that has the solution in it. But you know what, guys? The reality in the real world, the reality is that most physical problems do not have only one unknown function. Right? Usually there's many things there's many parameters that are floating around, many variables that you have to keep track of. All I have to do here to sort of show you how that could happen is suppose right next to this first one, I have another beaker that has some other amount of chemical pouring into it. And suppose that, maybe we now have like an R1 prime and a C1 prime, different rates and concentration here. And maybe this one's also leaking out the bottom at a rate of R2 prime and concentration of C2 prime. Now, if these two flasks are connected by a system where the fluid can flow between the two tanks, now all of a sudden I have two unknown functions and they are related to each other. How much chemical or what the concentration of the chemical is over here on the left side, if it's allowed to then go over to the right side and affect what's in the second beaker, then of course that means that B of T depends on A of T. And similarly, A of T depends on B of T. We now have more than one unknown function. And the point of it is that most mathematical problems, I'll just add this as a little background, most mathematical problems involve multiple unknown functions. Multiple unknown functions related by differential equations. And there could be more than one differential equation as well, right? So you could have several unknowns, several differential equations, and they are interconnected to each other. So this is kind of a visual that's sort of showing how that could come up in a physical problems, okay? And like I said, there's actually some examples in the book where they actually put some numbers into these values and actually set up a real problem that you can solve. I'm not going to go quite that far with this application for now. The point of what I've got on this board over here is just to make sure you're all appreciating that we might not just have one unknown function and one differential equation that we are trying to solve. We could have an entire system of these differential equations, and we have not learned yet how to solve such a thing. So that's what this chapter is going to be all about. Let me write down on the board a picture of, or a definition of what a linear system of differential equations is. So we'll start off with the definition here to kind of kick this off, get us all on the same page with this. So a linear system of differential equations, I'm about ready to define it here for you. A linear system has the form, and maybe we have n unknown functions. So we might have a bunch of differential equations for them. So maybe my first unknown function is x1 of t. And so the derivative of x1 of t might be a11 of t times x1 of t plus a12 of t times x2 of t and plus dot 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 plus a1n of t xn of t. And there might even be a term that doesn't have any of the x's on it. I'll call that b1 of t. I am going to write this out one time in full. It's a little bit long, so it's going to take a little bit of writing. Your wrist might get tired for a second as I put this down, but we'll only write this down one time. So that might be my first unknown function. The derivative of it is dependent not just on itself, but on all of these other unknown functions as well, right? So that's why this is a linear system. Then we would have maybe x2 prime of t. This would be a21 of t times x1 of t plus a22 of t times x2 of t and dot 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 a2n of t xn of t and then plus b2 of t. Something like that. And at the risk of boring you, don't wanna do that, so I'm just gonna go dot, dot, dot. And then we get down to the last one, we would have maybe xn prime of t. So notice I have a whole system of differential equations here. This last one would be a n1 of t, x1 of t, plus a n2 of t, x2 of t, and dot, 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 a nn of t, xn of t, plus bn of t. That is your entire system. You have n unknown functions here, right? So in this system, there are n unknown functions, namely x1 of t and x2 of t, comma, dot, 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 up to xn of t. I'm gonna slow down for a second to make sure everybody can write. I know I'm writing really fast. It's easy for me because the friction on the board is so minimal that I can like glide right across. You guys are trying to use these pencils and pens and so on. I know it's not quite so easy. So yeah, this is annoying to write it down too many times, but as you're gonna see in a second, it's gonna compress dramatically in just a second. Okay, so far is everybody okay? The goal, of course, is to solve for those unknown functions. And we've got n of them, and I would like to solve for them. To represent this better, I'm going to, first of all, I'm going to stop writing the of t everywhere. T is to be thought of as time. You should think of these as being unknown functions of time, like the amount of chemicals in the tank as a function of time. So that's my variable of choice. I do want to point out in chapter 8, in the stuff that we did on Tuesday and last week, the unknown function was generally written as y of x. I will get every semester a certain fraction of students who continue to use this in chapter 9. And I always have to strike it out and say, no, it's now x of t, right? So that's the thing to keep in mind. Our notation is shifting a little bit as we move into this new chapter. Now, I'm going to rewrite this in a nicer way. I promise it's less writing, using, as you might not be surprised, a matrix. We're going to express this in a matrix form. So let's rewrite in matrix form. We haven't seen a lot of matrices lately. We had that Wronskian matrix, I guess, in chapter 8, but besides that, there were no matrices there. So on the left side, I'm just going to have x1 prime, x2 prime stacked into a vertical column as a vector. So that's just x1 prime, x2 prime, dot, 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 dot. And then that equals, now on the right side, I promised there was going to be a matrix here, and you can probably kind of see what's going to make up that matrix. All of these aij's, right? So I have an A11, A12, and so on going across the first row to A1n. And then the second row is A21, A22, and dot, dot, dot to A2n. And we're going to just go dot, dot, dot in this whole big block. The last row would be a n1, a n2, and dot, dot, dot down to a nn. Now, each of those a's is getting multiplied by one of my x's. So a11 times x1 plus a12 times x2 and so on. That reminds me of doing a dot product the same way we multiply matrices together. So guys, we need to add a column here on the right that has x1 through xn in it. So that's just a column vector, and those are where your unknowns are being stacked up. Okay, so x1 through xn, and you can just check if you do these dot products, taking rows of A and dotting them with the column of x's, you're going to get the stuff that is multiplied together as a dot product on the right-hand side. The only thing I have not put in here yet are the B vectors that are kind of sticking out on the end over here. So I'm gonna add that as well, a vector that just keeps track of those B's, and there are N of them there. And again, everything you're looking at is technically a function of T. Excuse me. So that is a matrix representation of my system, but I'm going to compress it even more because this left-hand column looks like just a single vector. I'm going to just think of that as the derivative of an entire vector x. Okay, and then on the right side of the equal sign, I have my matrix. What do you suppose I'm going to call that? Capital A, right? Times, and then this column here is just the X column. And then we have a plus B as well. So this becomes a even nicer way of expressing our system. And the goal here of chapter 9, what we're going to be learning here in this next week or so, is how to solve for the vector X. So solve for X. And of course, that is a vector. So when I say solve for X, I'm actually solving for X1, X2, X3, X4. All of these X's are comprising that vector. So you're actually taking on a pretty big job there of working out the solution for X. Okay. So let's see. Notice that the matrix A is n by n. So we are looking at a square matrix here. That's good to keep in mind as well. And it turns out that learning how to solve this thing and achieving our goal is kind of hard to just jump into the deep end of the swimming pool for that. We're going to come back to that one on the very last class of the semester. So stay tuned. In a couple of weeks, I will come back to this full linear system and solve it. But for the next couple of classes, we're going to make this a little easier on ourselves by ignoring the B. Okay? I mean, you guys remember that that's what we did in the last chapter too. It's starting to become my signature method for solving everything. I want to solve L of y equals F. Well, start off by solving L of y equals 0 first, right? Solve the corresponding homogeneous equation. And then later on, there was a step 2 and a step 3, and we learned how to do the general one. But we started, right? We started with the homogeneous differential equation. So that worked out pretty well in chapter 8. So I'm going to try and do the same thing in chapter 9. I'm going to start by ignoring the B that is appearing here on the right-hand side. So another quick little definition to express that. So if that B vector is 0, and remember the B vector is really consisting of all of these entries. So that's B1, B2, B3, all of them are gone now. If they're all equal to 0, then we call the linear system. And you're going to hear this word again, homogeneous. All right, that word has been overused, I would say, for the last 13 weeks. We're going to use that same word in yet another context, homogeneous. So a linear system is homogeneous if it looks like this, x prime equals a times x. So there you have it. It's boiled down now into its simplest possible form. Okay? Somehow solving this should be easier than solving this. Oh, by the way, if you're just to give you a sneak peek of the last lecture of the semester, to solve this here, we're going to do a 3-step process. We're first going to solve the corresponding homogeneous system. Then we're going to learn how to find one particular solution to this one. And then we're going to do a step 3 where we add the 2 parts together. It's going to be deja vu of chapter 8 all over again. Okay, but for the time being, most of what we have to learn is just how do we solve this? X prime equals AX. But we are in a good position here. If the b is 0, guys, we are in a good position to use our linear algebra background. Okay, and let me show you why. I'm going to state a theorem here that will help us to take advantage of the linear algebra. So if I look at the set, capital S is what I'll use for this, of solutions, the set S of solutions to x prime equals a times x forms an n-dimensional vector space. It forms a vector space. The n that we're talking about, again, just to remind you, the n refers to the size of the matrix. It's the number of unknowns that we have in our system. So A is an n by n matrix. Notice it's a square matrix. Okay, so A is a square matrix here. And I'm claiming that these solutions do actually form a vector space. They are closed under addition and scalar multiplication. Let me just try and show you that. Closure under addition. So sneak a little bit of linear algebra into this conversation now. So closure under addition, which is what this is saying. How would that look? Well, we would assume that we have two vectors that are already in S. Let's say x comma y is already an element of S. So we start off with two things that are in S. And what I want to ultimately do is show that x plus y is still in S. That's what I'm going to try to do. Okay, so it's just the same approach we've used so many times. But before I write down x plus y, I just want to explain if x and y are in S to begin with, that just means that they are solutions to this. So that means, let's write it down, that is x prime is equal to a times x, and y prime is equal to a times y. So both of these things would be assumed as a starting point that would be true. Okay? And so then the question is, well, what about x plus y? Like, what about the derivative of x plus y? Is it still equal to a times x plus y? That's what element of S should satisfy. Well, we all know that derivatives respect addition. So I could just break this into x prime plus y prime. Guys, be sure you put arrows on these x's and y's. We've spent the last 2 weeks doing scalar functions, and so we've kind of gotten out of the habit of putting arrows on the vectors. But these are vectors again. We're now back in vector world. Okay, but x prime is ax, and y prime is ay. Just plugging in what's in the boxes there. And what do you suppose I'm going to do for the next step?
Pull out A.
Factor the a. Very good. Yeah, I'm going to pull out the a, and that's multiplied by the quantity of x plus y. And so let's take the big picture of it. On the left, I have the derivative of x plus y. And on the right, I have that it's equal to a times x plus y. In other words, it is fitting this system. The derivative of x plus y is equal to a times x plus y. And so this implies that x plus y is an element of S. Yeah, it is an element of S, therefore. So it is closed under addition, and that's a write-up that hopefully looks kind of reminiscent of how we show closure back in chapter 4 or whatever. All right, so we've got closure under addition. We also have to have scalar multiplication, right? So let me just say a quick word about that. Closure under scalar multiplication. For this one, just remind you that we have to have a scalar here, so I'll call it K. So K is my scalar, and I'm just going to see, and then we can just say, and X as above. We take the vector that we used in the addition part along with a scalar, and I just want to check what happens when I do K times X. Okay. This is the function of the hour, and I want to double check. Is it in S? In S means it's a solution to x prime equals ax. So let's take the derivative of it. Let's take the derivative of that guy and see what happens. What do you suppose I'm going to do first here? Anthony, I can't hear you. Product rule I could, although K is just a scalar. So if you have just a scalar, you don't really need the product rule. What can you do with scalars when you take derivatives? Pull them out. Yeah, let's just pull this thing out. Let's just pull the K all the way outside. So K comes outside of the parentheses, and we just have K times X prime. And then what do we have for X prime? Well, that was A times X, right? X prime is the same as A times X. We know that. And now normally we cannot switch the order of anything that involves matrices, but if K is just a number and A is a matrix, then there's no harm in moving the A and the K into the opposite order. So I'm going to switch those around. And the reason I want to do that is so that I can have the derivative of my Kx equals A times Kx. And so putting that together, again, this implies that K times X is in S. So it is closed under scalar multiplication as well as addition. And to be a vector space, of course, there's 10 axioms. But all of the rest of the axioms are just algebra axioms. Things like commutativity of addition, associativity of addition, all of that stuff works for functions slot by slot. It's not a big mystery. So we're really not going to focus on that. It's just getting the closures, which really makes it a subspace. That's really what we want. Edgar?
Is the zero vector also?
I was just about to mention that. The zero vector would be x equals 0. The zero vector would not have been a solution to this. If you put in 0 for x, and of course the derivative of 0 is still 0, you would have 0 equals a times 0 plus b. Well, that plus b would throw it off. And now the left side and the right side wouldn't work. And so if we were trying to go gangbusters and figure out how to solve this today, we wouldn't be able to use the linear algebra at all because we wouldn't even get past the zero vector check. So one of the reasons why we are choosing to focus on the homogeneous system is so that we will actually have a vector space. And you can check if you put 0 here and here, it works, right? So the zero vector check does pass. I probably should have written that down, but it's not necessary to check the zero vector. If I've checked the closure under addition and scalar multiplication, that's all you have to do for a subspace. The zero vector check, if you remember, it's a good review for the final, I guess. The zero vector check is used to disprove that something is a subspace. So if I wanted to show that this wasn't a subspace, I could use the zero vector check. Right. Good questions. And does anybody else have any questions so far? Where am I at here? Oh yeah, okay. So I didn't justify the dimension here. So we're not going to prove that. That's much more technical. But it will be n dimensional, assuming the matrix is n by n. And by the way, for most of the problems I'm going to ask you to do in this chapter, n is going to be 2 or 3. If I get really bold, Or if you guys get me irritated, I might go to n equals 4 or 5, or I could make a special exam for anybody who wants one. So anyway, but normally n will just be 2 or 3. That's usually big enough to make things work. But we do have to pause therefore and ask a question here again, which is that if this is n dimensional, that means my basis has to have n solutions in it. And I need to know how to test that basis for being Li again. So just as in the last chapter, we had to stop and figure out, well, how do I know if my functions are going to be Li or not? We actually have exactly that same question here. So I'm going to ask that question and try to answer it. So please bear with me. We do have to spend just a little time here at the beginning of this chapter just getting the setup of this whole thing. I promise that very soon everything will become computational. We'll have a matrix in front of us. We'll start crunching the numbers and calculating stuff. But at least to get it set up, I have to spend, I don't know, whatever this is, a half hour or something, kind of just getting the background of it so you kind of know where this all fits in with the theoretical stuff too. So let's ask this question, which is the following question. If it's n dimensional, then I gotta know if my n vector functions are gonna actually be Li. So how can we tell if n vector functions? See, we have not worked with vector functions before. Today's the first day for this. So we don't have any past experience to help us with this problem. The vector functions are x1 of t, x2 of t, and ... up to xn of t, right? And let's put that into a set. How can we tell if that set, x1, x2, x3, and so on, is Li? I'm going to need to be able to do that if I expect to have a basis for my solutions to my linear system. Everybody kind of see where we're going with all this stuff? The goal, it's not, let me just back up for a second. What is the goal? The goal is going to be to solve this system, okay? If you believe the theorem is going to tell us that if we can come up with n basis solutions, if we can just find specifically n of them, which is usually going to be either 2 or 3. If I can find 2 or 3 solutions, then I can span the entire solution set with that basis. Everything that solves that system will simply be a linear combination of those basis solutions. So this is all kind of very similar to chapter 8. It's just that now we have vector functions rather than scalar functions. In chapter 8, we had y1 of x, y2 of x, ... up to yn of x, and I asked you the exact same question. How can we tell if these are Li? What was the answer in chapter 8? Oh, come on, it hasn't been that, it has not been that long. What's the test for Li for functions in chapter 8? I think, was it the Wronskian, right? There was this Wronskian, you lay these vectors into the rows of a matrix, you take derivatives, make it into a square matrix, and just do the W test, is what I called it, right? There was a Wronskian test. So we had a test for that, and we even did a group work where you guys actually went through the steps of why that Wronskian test works, right? So we're at the same crossroads here, except that these are not scalar functions. These are actually, each one of these entities that are filling up this set is an entire column, right? Because this has got a vector on top of it. It's an entire column. So it turns out that the answer to how we're going to test functions for Li in chapter 9 is actually going to go by the same name. We're going to call it a Wronskian again. I'm going to refer to this as a Wronskian. However, this is not the same Wronskian. So I have to warn you, there are two different Wronskians in this class. This one is actually the easier one, the one I'm about to show you. Now, the one that we learned in chapter 8 was kind of a pain. We had to take derivatives and do all that stuff. We don't have to do that here. The W here, so this is W of x1, comma, x2, dot, 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 up to xn of t is going to be a determinant again. So just like in chapter 8, we make up a determinant, but how we do this matrix. So again, in chapter 8, we would lay the scalar functions on the first row and then start taking derivatives. That's not what we do here. All we do here, my friends, is we just literally lay the x1 and the x2 and so on into the columns of this matrix as is. We just lay them there as is. We don't have to take any derivatives. We just lay them there as is. And then our theorem, which is our W test, is going to look very similar to the one we had in chapter 8. So let's just write this down as well, but this is gonna maybe feel like deja vu from 3 or 4 classes ago. So the way this W test works is if there is a value of t, say t naught, such that W of W of x1, comma, x2, comma, dot, 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 up to xn. Be sure to put arrows on those functions, guys. Those are vectors, not scalars. So W of x1, comma, x2, comma, dot, 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 up to xn of t naught is not 0. So it's the same exact theorem. Should look very familiar from just a chapter ago. If we can make this Wronskian not 0 for even one value of t, then my functions x1, I'm going to make a set of x1 and x2 all the way up to xn. That set is Li. I'm going to do an example in a second, but if these functions are Li, guys, there's n of them there. My vector space is n dimensional. So guess what? This becomes your basis. This becomes your basis, and that means that any solution can be made out of those as a linear combination. It's so nice. It's so nice. I've just reduced this problem of trying to find all of the solutions to my linear system, of which there are infinitely many. I have shrunk that problem down into only needing to find n of them and just test them to be Li. As long as I've done that, I'm going to sleep well at night, that I have a basis and that I can write all the solutions in terms of those. Yeah, that's really a powerful idea. Let's do, I think I have an example in my notes here I wanted to try. Oh, by the way, the proof of this is almost exactly the same as the one in the group work number 12 that you guys did. About a week ago, I had you work out the proof of the W test for scalar functions. Well, this is actually an even easier one to prove because there's no derivatives. You don't have to take any derivatives here. And the proof is almost the same. I think I'll omit the proof this time through and just get right to an example. So let's do an example. Okay, so let's ask this question. Is the set, and I'm going to make 3 column vectors here, t plus 1, t minus 1, and 2t. That's the first vector, comma. And then my second vector is going to be e to the t, e to the 2t, e to the 3t, and then comma. And then my third vector is going to be 1 sine of t and cosine of t. And I'm gonna take that set and I'm gonna ask you, is that Li? Or LD? Linearly independent or linearly dependent? That's the question. So this first column is like my x1, and then the second column is the x2, and the third column is the x3. They're all functions of t, and they're all vectors. These are vectors. Okay, guys getting comfortable with this? The notation here? You see, I can already put these into a matrix without having to take derivatives. In chapter 8, we might have had just one scalar, and one scalar, and that's not enough to make a 3x3 matrix. So we had to take derivatives to get that to happen. Here we don't have to do that, right? Let's just jump straight into the solution, guys. It's just ready to go as is pretty much. So I'll do the solution right here in blue. I'm going to set up a W for you. W is the Wronskian, and this is the determinant of how do I make my matrix here? Well, all I have to do, guys, is lay the columns that are listed there into the columns of this matrix. So the first column will be t plus 1, t minus 1, and 2t. And the second column will be e to the t, e to the 2t, e to the 3t. And the third column will be 1 sine of t and cosine of t. Okay. Excuse me. Now, this is a 3x3 determinant. We've got lots of practice with that. We could solve this determinant by using the arrow method, or we could do a cofactor expansion. That would be fine. Either way, the matrix is not terribly nice because it's got no zeros in it anywhere. If I was going to do cofactor expansion, there really isn't a preferred row or column to do the expansion on. But we could do that. We could do that, but let's just remember what the W test tells us. It just says if there is any value of t whatsoever, even just one value, that makes that not zero, we win, right? We would win. So what we can actually do if we want is we can decide to gamble. Instead of writing out the whole big thing with like 6 arrows or whatever, with some big long expression with t's in it, we can take a guess and we can just try a value of t naught that we think might work. And I don't really have good advice as to like, well, what's going to work and what's not going to work. It depends on the problem. But I do want to pick a t naught that's easy to plug in. Can somebody think of what's your favorite number to plug into a function normally? What was that? 0. Okay, I would probably pick 0. I thought you said 1. 0. I would pick 0. And let's just try it. Let's just try it. Let's just do that. Let's just kind of gamble. So I'm going to evaluate all 9 of these entries by plugging in 0. So if I plug in 0 for t, I'll get a 1. E to the 0 is 1, and we have a 1. And then when I plug 0 here, I'll get minus 1, 1. Sine of 0 is 0. And then 0, e to the 0 is 1, cosine of 0 is 1. So there's your resulting matrix. So you're allowed to do that. You're allowed to plug in a value of t naught ahead of time and just calculate it and see what happens. If you now take this one, it's a lot easier to do the arrow method on it, right? And so I did it with that particular value. Let me write down the 6 arrows. The first diagonal would be a 1, and then we would have a 0, and then we would have a -1, and then we would have a -0, and a -0, and a -1. So it actually comes out to 1. If I did that right, if you clean up that all those minus signs and everything, you should get 1, which is not 0. So guys, we have stumbled upon a value of t naught. The first thing we tried, it worked. It worked, and so the answer is Li. So by the W test, Li, I'm gonna be a little brief because I don't have a lot of room to write there. So I would get Li out of that. Does everybody see that? Let me ask you a question though. If I had calculated that determinant and gotten 0 right now, what would you have me do if I plug in a value for T naught and the Wronskian comes out to 0, the W comes out to 0? What would I then need to do? One more time?
That's another.
Try a different number. Right, I would try, maybe we just picked a bad number, right? We only have to find one value that works. So if we had plugged in 0 here and gotten 0 for the W, then we could just try a different number. But whatever the second easiest number is to plug in, we could try that one. And if that one's not 0, if that W is not 0, then we're still good, right? At that point, the functions are still Li, right? What if we got 0 the second time though? Not really. No, sorry to say. Yeah, no, we have to live with this matrix as is. Okay, so I tried a value of T and I got W to be 0. Then Bond tried a value of T and that also gave 0. Then what are we gonna do next? What's that?
I say keep trying.
Try another value of T, right? Try a third value. Okay, great. And if we get a non-zero Wronskian, we win. It's Li at that point, right? So at any point, if we succeed in finding a value of T that's not 0, then the functions are Li. Because you only need one value of T naught to make that Wronskian 0. But you know where I'm going with this. What if I got 0, Bond got 0, James got 0, and let's say we do this 3 or 4 times and we're just really getting sick of this problem, right? At some point, you're going to kind of get tired of it. You're going to start, I wonder if it would always be 0. Well, that's the LD outcome, right? Maybe we should look at an example of when it would definitely be 0 and the Wronskian would be 0 and just take a look at how we would have to approach that. So let's do one more example and then we're gonna be pretty close to done with this. Done with the setup part of all of this stuff. So let's just do one more example. I'm gonna make it really not too complicated. So is the set of, let's go with T squared and 5T squared here. And then over here, I'm gonna go with cosine of T and 5 cosine of T. Is that Li or LD? Just pick a little problem. This is only going to be a 2x2 example. Okay. And since it's 2x2, it's almost too obvious, but I just want to kind of play dumb on this and just like go through the process to see how we would do this. So the solution, would be to write down W, which would be the determinant of T squared and cosine of T, and then 5T squared and 5 cosine of T. Right? And we could, at this moment, say, well, what's my favorite value of T? So we could evaluate, when I draw this bar, I mean evaluate it. So taking the same approach that we did on the last example, I might try 0. If I plug in 0 here, and so this would be, if I plugged in 0, this would be the determinant of 0 and 1 and 0 and 5, I believe. Because cosine of 0 is equal to 1. And sure enough, you work that out and you get 0. Right, so the first value of T we tried, we lost. So that means we come back over here and we say, I'm going to start over with a different value of T. So we could try again. Let's just come down here. And my next favorite value of T, I'm going to take the same matrix. I'm going to take the same matrix. I'm going to take T naught equal to 1 because that's probably the second best number that I can think of. So in this case, we would have the determinant of 1 cosine of 1, 5, and 5 times cosine of 1. So I'm just putting in t equals 1 everywhere. And if you look at this 2 by 2 determinant, you get AD minus BC. Yeah, cancels out to 0 again. Right? So we tried 2 different values of t, and both times we kept getting 0 so far, which is not good because we were hoping that these functions were Li. But after doing this, say 2 or 3 or 4 times, we might start to get suspicious that we're always going to get 0. That there is no value of t naught that's going to rescue us here. And so the question is, what do we do? Do we just report back to our professor? Oh yeah, I tried 100 values of t, none of them worked, right? The mathematician is not going to ever be happy with that kind of a reason, because I'm just going to say, oh, you didn't try 101 values of t. Maybe the next one you try is going to work, right? And you just got really unlucky 100 times. So instead, what you would need to do now, if you have kind of figured out that these functions are probably LD, what you need to do then is you need to actually do the determinant with the t's still in it without plugging any number in. Because I can always say, oh, well, you just didn't pick the right number, right? So to keep that from being a concern, the way around it is to say, I'm just going to do W with the t's in it. So what we can do here, so here, for general t, my W, which is the determinant of, what is it, t squared cosine of t, 5t squared, and 5 cosine of t. Instead of plugging a specific number into this, we can just leave it with t. Do AD minus BC. So 5t squared cosine of t minus 5t squared cosine of t. Aha. Aha. Regardless of what t is equal to, this is, of course, always just canceling out to 0. That's for all t. And so thus, LD, right? Basically, that means that these functions would be LD in this case. You see what I mean?
If it's 2 by 2 matrix, I think this is easier.
It's too easy. Yeah, you probably can look at it, guys. Can you just kind of look at it and see that these are kind of like scalar multiples of each other? Right? I mean, actually, the second row is just 5 times the first row. When you have a little 2 by 2 matrix, you can usually just eyeball it. But I want you to know that for a larger matrix, that might not be just staring at you. You might actually get fooled by it for a minute. You might actually try 2 or 3 values of t, thinking you're going to be able to get a non-zero Wronskian. But then at the end of the day, there might actually have been a subtle linear dependency among those rows or columns. And so I didn't want to do a real big example here, but this is to give you the idea of what happens. If you start plugging in value after even just 2 values, I'm usually getting pretty suspicious, right? If you try a couple different values and you're getting 0 every time, then the question becomes, maybe these vectors are actually LD. Okay, so far so good? Okay, I'm going to do one last thing before we take a break, and then I think we'll spend most of the rest of the class going back to chapter 8 to look at the homework and the group work that I brought. But I have one more thing. I have to show this to you because it is super exciting. This is going to be very exciting. At least for one person in this room, this will be very exciting, which is, so I've asked the question, how do we test our solutions for being Li? We now have the answer to that. But the question is, how are we going to come up with our n solutions in the first place? I mean, if we want to have a basis for the solutions to our, I'm talking about this box right here, right? This is supposed to be an n-dimensional vector space. I've now given us a tool for testing the Li of our solutions, but how do we get those solutions? So I'm going to finish this part of our class by answering that question, and you're going to love the answer. So here is the question first, and then the answer, which is, How can we find? How can we find n linearly independent solutions to x prime equals a times x? And remember, A is this n by n matrix, right? It's a really cool answer. And the answer, believe it or not, involves, the reason I like it so much is it involves linear algebra and it involves something we've studied earlier, not that much earlier though. I think this is still gonna be something pretty fresh, which is that this is related to the eigenvalue, eigenvector pairs of A. Remember, this is a square matrix, and so we have eigenvalues and eigenvectors. All that stuff we did in chapter 7, yeah, we need it. We're gonna use it. If you've forgotten how to do the characteristic equation, do those null spaces and stuff, it's gonna come rushing back to you now, right? We're gonna need it heavily in the rest of chapter 9. The answer is, suppose that lambda and V is an eigenpair of A. So suppose we have that. Let me just remind you what that means. This is a good time to review for our exam in a week. What is the all-important equation that goes along with having an eigenpair?
A is equals lambda times the vector V.
AV equals lambda V. Very good. It is the most important equation in chapter 7. I've said that 100 times. And we're gonna see why it's relevant right now. Here is what we're going to do, guys. I am going to concoct a solution to our system of differential equations right now in the following form. X of t equals, look at this, e to the lambda t times v. That's going to be the answer. That is going to be the answer, but I'm going to show it to you. I don't want anybody to take my word for this one. This one's too cool to just take my word for it. So guys, it is so easy to write down solutions to your system. All you got to do is take your matrix. It's going to be 2 by 2 or 3 by 3. Find the lambdas, find the v's. You already know how to do that. That was chapter 7. And just throw the lambda there, throw the v there. You've got yourself a solution. If you've got n eigenpairs, then you'll have a whole basis worth of solutions to build out your general solution. Right? So let me just show you this. I'm going to just check it real quick. And then we'll probably wait till next week to get into any examples of this, because at this point I'm about halfway through chapter 9 already. We're going pretty fast. So let's just check this. If I take the derivative of this, let's take the derivative, the x prime of t. In other words, I want to take the derivative of this thing right here. Now, the v is just a constant vector. It's got numbers in it. The t occurs right here. The derivative of e to the lambda t would be lambda e to the lambda t. And then the v is like a constant that just comes along for the ride. So you just copy that constant right down. And I'm sure the minute that I do that, everybody can see right away, oh, we can put the lambda right next to the v, because if I see a lambda v anywhere in my future, that can be thought of as AV. So I'm going to do that. I'm going to rewrite this as AV. So that's coming from the most important equation in chapter 7. AV equals lambda v. Now I'm going to move the A out in front. So I can switch the order there, because everything else, the e to the lambda t is just a scalar. So I can put that with the v. And look at that, my friends. This is just A times the x that we started with. I guess I called it x prime of t here, so I'll call it x of t here. X prime equals AX. It works. If you construct this gadget right here, right? Then it turns out that it will solve the differential equation. So easy, so nice. So, I'd like to do an example, but yeah, I think I can. Shall we just do one really quick example? Just show you how this works. Oh, I wish I had an actual. Give me a second, because well, no, I have an example. Just use this example here. I might skip the eigenvalue, eigenvector calculation, just show you. I just want to show you how simple this is. Okay, and then we'll take a 5-minute break or a 10-minute break. So example. Here we go. Solve x prime equals a times x, where a is equal to, I'm going to give you a little matrix here, -2, -7, and then -1 and 4. Okay. Solution. This is a 2x2. It is pretty easy to find the eigenvalues and eigenvectors. I think for the purposes of this example, I am not going to go through all that checking because we've practiced this a lot recently. So I'm just going to say we can check that the lambdas are, lambda 1 is 5 and lambda 2 is -3. Just take my word for it. Actually, you don't have to take my word for it. You can check these now. The trace of the matrix, if I add the diagonal, it adds up to 2. So these lambdas have to add up to 2. The determinant of this matrix is actually -15. So the product of my lambdas should be -15. So it seems like those are going to work. And then, of course, you have to then find the eigenvectors. Each of these is going to pull one eigenvector. Let's call this one V1. And then down here, we're going to get another one, which will be V2. And so just again, I'll let you check this. I don't want to do a big null space right now. I want to just get to the new material of this. For lambda equals 5, you'll get an eigenvector of -1 and 1. You can check that. And then for the other eigenvalue, which is lambda equals -3, you'll get an eigenvector of 7 and 1. Okay, so just take my word for that part. You guys are well versed on how to do that piece of it. But once I've done that, guys, I can now write down the whole solution. Ready? X1 of t is going to be, if you believe this thing here, which you should, because I proved it. It is e to the 5t times the vector -1, 1. And x2 of t is e to the -3t times 7, 1. Okay? If anybody's worried if these would be LD potentially, I can put that to rest really quickly. Right, I can very quickly take the determinant of this little 2x2. Now, how do I fill out the matrix? I just put that e to the 5t inside the slots here. So I'll just have -e to the 5t and e to the 5t in the first column. The second column will be 7e to the -3t and e to the -3t. I'm gonna gamble t0 equals 0. See if we can get it to work. All right, so I'll go ahead and do that. Let me get this camera over here so people can see it better. If I put in 0 for this, everywhere I see a t, I'm gonna get -1 and 7 and 1 and 1, right? E to the 0 is just equal to 1 everywhere. And if I do this little 2x2 determinant, that is not 0. So the W test passes nicely. That means that my X1 and X2, they are Li. right? And it's a two-dimensional solution set because this is a 2x2 system. It's a two-dimensional solution set, and I have two linearly independent basis vectors. So guess what? They span the whole general solution. So what's the final answer here? The general solution, let's write it down. X of t equals C1 times the first solution, which is e to the 5t times -1, plus C2 times e to the -3t times 7 and 1. And that would be already the final answer. That's the general solution.
Sweet.
It is really cool. We have to remember how to find eigenvalues and eigenvectors. I kind of shoved that part under the rug. But then we build these solutions exactly as I explained here. And we can do our W test. Next week, I'll explain that you don't really need to do the W test on this type of situation. But then from there, you can go right into the general solution here. Just write it down immediately. Any questions? There are a couple of questions you probably would have, but we're not going to answer them now. But I will ask them for you if you don't mind. We did see, did we not, in chapter 7, that sometimes the eigenvalues or eigenvectors would be complex numbers?
Yes.
But you can imagine we're not going to be real happy putting complex numbers up here and these exponentials and so on. We're going to have to deal with that. So next week we'll talk about that. The other problem is that we also have seen in the past that our matrix is sometimes defective. If I need n solutions here, that would require me to have n, linearly independent eigenvectors. Everybody's got to pull their weight. So we're going to see next week as well that when the matrix is defective, it's not quite such smooth sailing. So a couple of lectures next week to kind of talk about this, but we've made really good strides into how to solve linear systems of differential equations already. Are we good? All right, I have 5:13. Let's meet back up at 5:23. I'm going to answer homework questions. There's already one on the board. I've also got a group work to practice the variation of parameters. So let's take a little break. Thank you.
Was that? Yeah, it's like.
But that's a little
I like
hard.
walking past Oh,
I'm thinking.
You know, there's like a max time.
yeah. See.
I've been so busy, I'm just like.
Let's take it. Where do you usually park the charger burn?
Back there, like on.
Which one?
James Drive.
Jim Drive.
Yeah, what's the street name?
And then you have to come.
It's
Let me get out your glasses.
It's like, okay.
Yeah, see, California.
No, it's like. What is that? We know where the gym
I'm
is?
actually not familiar with the, like northern, western side of the campus.
So we're here.
Uh-huh.
We'll have to walk back there.
Oh, okay.
Yeah. This is like.
Where's my north arrow? Oh, and I twisted, that's like.
Oh. And my phone's just being good.
Mhm.
It's like, it's very.
That doesn't know where it is.
No, it's lost. Since I never used GPS on my phone. It's so annoying. When you're saying it, the hard is
Should be helping that out with
Like, worried about the study exam, it's just the coordination. And I'm not gonna be like,
Yeah.
we just gives us trivial stuff on the purpose. It's this. Freaking stuff.
So yeah, this is all computational. I feel a little bit better. but-
That's why I asked that question.
Oh, really?
No, like how people are on this test compared to.
Oh, this is all computational.
Yeah,
Yes.
yeah.
Except for
He didn't
six.
give a straight answer.
Say, I'm going to say.
He's like, some people do better on. It's like, oh.
So.
Yeah, raise your hand. Is that the kernel? Wait. I forgot.
Yeah. Oh, yeah.
Linear transformations. That's, I thought that was last test.
Well, I think it's, we can sit.
With the nominal stuff, right?
Yeah, but we also use linear transformation right there. It's explained to us on chapter 6, we're still going to be using. Now.
7 is lambda, 8 is annihilator.
That is
This.
But, yeah, I think we still. Still.
Just hanging on.
Last time, then he went over and.
That's like part of it. Tires.
Yeah, you're under. 55, no, 65. Okay, can you pass the class with a 60?
Yeah.
Oh, really?
Yeah.
Well, a 65 is a C. You did the credit at a C.
Yeah.
Yep.
So,
Sometimes they're like, oh, you need to pass this course from the C or better.
I still consider it.
Oh.
Important to me. I think it's still good. It should be fine. Yeah, I don't know. It seems honestly possible.
Let me think.
I think
Yeah,
it'll
they-
be fine.
For some courses, they have. You know, yeah, most of them are 75.
I don't know.
You don't know what you're doing in the class.
Because whenever I go on there, I never bother waking up. I know it's.
Is that just made for yourself?
Yeah, I just don't do it. I just don't do it. That's, yeah. Yeah.
Don't get caught up in the minutia. Getting down or something.
That's actually my other tech, my other.
Yeah,
process.
that's right. That's it.
I'm really sick. I'm gonna have that exam next week. So that's really tough.
With the C. Yeah, see what you say? See more better. There's a C, and it's like. Allow you to.
Say, bro, are you looking at C minus?
I think it's those. We should be-
With an A- or better.
But you know. See, they really do that, they move on to the. So like. This is like one right now. That's why I did. But then I did that. I did some of these classes. So math 170, I did that, like, went to my last time. Once. Better than that. Take it over to some. I already took it, but I took it like last semester. And. So, is it better or if it's not? Maybe I'm each engineering courses. Always.
I think it's a lot. How is it possible?
Decent now.
Every year. Every year.
About 2 years. Technically. That's
One hour.
one step. It's the metaphor.
One day.
Metaphor for climbing down.
Yeah.
And then just keeps you more excited. Or high blood pressure.
Yeah, I'm like, that's just like so bad. They don't get break anymore.
Why is this love jam for us?
Um,
I don't know why.
I appreciate that.
Oh, yeah.
Yes.
Because I'm on the bus, you don't really have like.
Hello. Getting about as much sleep as I am, it looks like, maybe even less. All right, guys, I think I'm gonna go ahead and pick things back up. We've only got about 25 minutes or so to go, not too long. We're gonna spend the rest of today going back to chapter 8. I'm gonna help you with the problems from the homework that are on the board over here, and then with whatever time is left, I have a group work for you to practice both the annihilators and variation of parameters method, and in particular, deciding which method to use, which is something that you definitely want to be thinking about. So, but let's start with the homework first, so I can make sure that I helped you out with that one. Number 30 is for tonight's assignment is this one right here. It is a third order differential equation, so y triple prime, and then plus 2y double prime minus 5y prime minus 6y equals 4x squared. And so we know the 3-step process, hopefully, for doing this. The first part of it is to just ignore the 4x squared and find the auxiliary equation. If you need to take an intermediate step and write down the D notation for the left side, you can. But I think after you've done this for a little while, you start to get comfortable with just jumping straight to this equation. 3 derivatives comes down to r cubed, and then plus 2r squared, and then minus 5r, and then minus 6. And then we're going to set that equal to 0 when we're doing the auxiliary equation. And now we already come to what I think is the hardest part of this question, and probably why it ended up on my board over here, is that we have to find the roots of this cubic equation. There is no formula for the roots of a cubic. Well, there is a formula for it, but it's very complicated, and we're not going to use it. It's not something we generally can just use directly. So finding the roots of this is a little tricky. I want to give you a hint, however, that the candidates the candidates for the rational roots. I don't know if you remember rational numbers, those are the numbers that are just expressible as fractions or whole numbers of fractions. They are always divisors. The candidates are the divisors of the constant term. So I learned this in high school. I don't know if these days are doing much on this anymore, but it's a really handy thing to know. If you look at your constant term, which is 6, and you think about what numbers divide into 6, well, those would be 1, 2, 3, and 6, and they're negatives. So -1, -2, -3, and -6. Those are the only candidates that could possibly be the roots of this equation, unless the roots are irrational, in which case it's super impossible to expect to find them. You wouldn't get that from me on a by hand exam ever, right? You would have to have a computer at that point to find the roots. So the candidates here, guys, are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. And what you can do is just go through one by one and test all of them. You are hoping to come up with 3 roots because it is a cubic equation. So if you did manage to get 3 values of r that worked, you could stop at that point because you cannot have more than 3 roots for a cubic equation. So for example, you could try plugging in r equals 1. If you do that, you get 1 plus 2 minus 5 minus 6. Well, that does not work. So 1 is not a root if you try plugging in r equals 1. Then you could try -1. If I put in -1 here, I'll have -1 plus 2 plus 5 and then minus 6. So I'm putting in a -1 for r. And actually, when you simplify that out, you actually do get 0. That actually is a root. Okay, so now if you want, you can just continue with the other candidates and look for the roots from the remaining 6 candidates here. But there is another thing you can do. Once you find one of your roots, you can do this so-called long division of polynomials. Dare I bring you back to your high school algebra days? Let's see. I sometimes forget how to do this myself. R cubed plus 2r squared minus 5r minus 6. You just divide it out by so you found the root of -1. That means that there will be a factor of r plus 1 in the factorization of this thing. And you could just do long division here of polynomials. Have you guys done this before?
Yeah.
Well, somewhere back in the distant days. So, you look at the r and the r cubed, you say, well, what would the quotient be up here so that this times this equals this? Well, you'd have to have r squared. So r squared is going to multiply by r plus 1, and it gives you r cubed plus r squared. Then you just subtract. You subtract to cancel those r cubes, and 2r squared minus r squared is just r squared. And then we just pull down. We pull down the rest of the terms there, and nothing has happened with those so far. And we start over again with this new remainder, and we look at dividing it into r plus 1 again. Well, the r here and the r squared in the remainder suggests I need to put another r on top so that I'll get r squared plus r. I'll go ahead and do that. R squared plus r, and I subtract again. And when you subtract again, now you have -5r, and you're subtracting another r, and they bring down the -6 as well. And you can see how many times does r plus 1 go into -r minus 6? -6. No, is that many times. Okay, and this should go evenly into your, the thing you're dividing by. You shouldn't have a leftover remainder here, because this should be a factor of the cubic equation. So what we can say is that r cubed plus 2r squared minus 5r minus 6, it is equal to r plus 1 times r squared plus r minus 6. So you can just take that factorization And now, instead of continuing to test these other candidates, if you prefer, what you can do now is just factor the quadratic that you've obtained here. And that's going to factor as r plus 3 times r minus 2 in this case. All right, and so the roots that you get are -1, -3, and 2. Those are my 3 roots. And so I can write down the complementary function. We have no repeats here and we have no complex numbers. So this just becomes, C1 e to the -x plus C2 e to the -3x plus C3 e to the 2x. So we can just copy that down as our complementary function, and all of that is step 1. Most of the hard work is just coming up with the roots of the equation. Go ahead.
So for the x squared, should it be like r cubed like on the side?
Are you talking about this thing?
Yeah.
So the right-hand side has nothing to do with what we've been talking about so far.
Saying like when you apply this formula, shouldn't you have like r cubed on the side, like that would give you 3 zeros?
Not yet. That's step 2. We're coming to that. In step 1, I'm just literally thinking of this as 0. I totally ignore this and I just find the roots of the homogeneous auxiliary equation. But I know what you're talking about. That's coming next. Yeah, so when we go to step 2, guys, this is where we do the annihilator, right? So the annihilator of the right-hand side. What is the annihilator of 4x squared? B cubed, right? 3 derivatives. Remember, the 4 doesn't matter. It's really just x squared. And I can annihilate x squared with d cubed. And this gives me new roots. Keep in mind, these are the old roots. The original roots from step 1 are the old roots. These are now the new roots, and they are 0, 0, and 0. I think that's what you're talking about. Yeah. These roots did not appear before, so I'm going to kind of write down the particular solution. Y sub p of x, it's going to be, what would it be, guys? A plus b x and cx squared. Exactly. So there you go. That's going to be the form of the particular solution. That's the form of it. What I have to do though is plug this into the original problem to solve. Now we have to solve for a, b, and c. Okay, so that means I need to take 3 derivatives of this, but the good news here is the derivatives are easy to take because these are just simple powers of x here. So I'm going to go ahead and take 3 derivatives of this. The first derivative is going to be b plus 2cx. And then the second derivative, if I take another derivative, I'm just going to get 2c. And then 2c is a constant. So if I go to the third derivative, which technically I should, it's just going to become 0. Those are the derivatives of our particular solution. And what we will now have to do is plug those derivatives into the left side of our original differential equation. Okay, so I'm going to do that next. Let's come back over here and see how that looks. Y triple prime, well, that was already just 0. So now I'm doing what I often will write plug in at this step. Plugging in all these derivatives. So the y triple prime is just 0. And then I have plus 2 times y double prime. Y double prime was 2c. And then we have minus 5 times y prime. Y prime was b plus 2cx. And finally, minus 6 times the original y, which is a plus bx plus cx squared. And all of that should end up being equal to 4x squared. Okay. The trick to this is matching up the different powers of x on the left side and on the right side. Let me gather up all of the terms that are just constants on the left. I have 4c here, and then I have minus 5b, and then I have minus 6a. So all of that could be thought of as the constant term. And then the x term is negative, let's see, 5 and 2c, that's negative 10c. And here's an x as well, negative 6b is multiplied by x. And then that's it for the x's. The x squared term is just minus 6c x squared. And so we have to set that equal to 4x squared. And so what do we get? We get that this coefficient, there's no constant term on the right side, so the left side coefficient has to be 0. This also has to be 0 because there's no x's on the right side either. And this one, negative 6c should equal 4. Just to match the coefficients. Does everybody see how I'm doing that? So you put all the constant terms together on both sides, match them up. Put all the x terms together on both sides, match them up. And then all the x squared terms together on both sides, match them up. And so in this case, negative 6c should equal 4. So your first calculation will be that c is negative 2/3. I then have to take that information and go to the x coefficient. So negative 10 times c, which was negative 2/3, minus 6b is supposed to be equal to 0 here. Let's see if I can figure that one out. 20 over 3. And then I'm going to end up dividing by 6 when I solve for b. So 20 over 3 becomes 20 over 18, which is 10 over 9. So this is just basic math, guys. I'm not going to belabor it. B is going to equal 10 over 9. And then last but not least, we have to go back and solve for a from the first part here. So let's see, 4 times negative 2/3 minus 5 times 10/9 minus 6a. That's supposed to equal 0. Looks like we're going to have some fractions. I think the answer is 37 over 27. This is gonna make my head hurt. 8/3 minus 50 over 9 equals 6a. So if I make a common denominator of 9, I have negative 24 minus 50 equals 6a. This is negative 74 over 54 equals a. That's 37 over 27. And that would be with a, what's that? Negative 37 over 27, yeah. Yeah. So that's the a value, excellent. Okay, so that's just mundane calculations. And so then the particular solution, let me come over here and write down the final answer. The particular solution is negative 37 over 27, and then plus bx, that's 10/9 of x. And then minus 2/3 of x squared. There is your particular solution in this case. And the only thing left to do is write down step 3, which is where you just literally, I'll just do it right here. Step 3, as you remember, we just write down y of x equals y sub c of x plus y sub p of x. Right. Quick reminder, we use the annihilator method here mostly because we know how to annihilate 4x squared. Also, the new method we learned on Tuesday, which is the variation of parameters method, we only learned it, if you remember from Tuesday, we only learned how to do variation of parameters for a second order differential equation. So this is third order. You're not going to be thinking about variation of parameters for something like that. Make sense? Any questions on that problem? Okay, let's look at 42 as well. That's also up here on the board, and then we'll be pretty well finished for today. 42. Let me write it down. D squared plus 4 times D minus 2 cubed of y equals 4x plus 9x e to the 2x. Oh, and in this problem, they just say find the appropriate trial solution. What that means is they want you to give the form of the trial solution, but you don't have to solve for the constants, which, as you can see, is a big chunk of the work. So it's going to make this one nice. This is going to go real easily. The first step is to find the auxiliary equation again. On the left side, I'm going to turn all of the D's into R's here. I'm going to go quick, guys, just so I can finish up well ahead of schedule. So the roots are plus and minus 2i along with 3 copies of 2. Be sure to write down those repeats so you don't miss something later. So these would be the roots, 5 roots here. This is a 5th order differential equation. I would hate to think about solving for the constants in this case, because you'd have to take 5 derivatives of whatever you came up with, right? But luckily we don't have to do that. Okay, so let's write down the complementary function here. Can somebody tell me the first term?
C1 cosine 2x.
Okay, C1 times cosine of 2x. Can somebody else tell me the second term? C2 sine of 2x, good. Somebody else who I haven't heard from want to tell me the next term? Say again? I don't think so. That would be if 0 was a root. One more time? C3e to the 2x. Awesome. Okay, because the root is 2 here. Okay, somebody else who I haven't heard from want to tell me the next one?
C4x.
C4x e to the 2x, right? All right, great. And do I have another volunteer?
C5x squared.
C5x squared e to the 2x. You guys are gonna be ready for my 16th order differential equation on your exam next week?
Nope.
You can't just write ... Yeah, right. That's probably the way to do it. Anyway, so that's step 1. Okay. Now for step 2, we have to think about an annihilator for the right-hand side. Okay. Now, I don't have the table of annihilators in front of us here, so we might have to wing it a little bit, but let's see what we can do. Does anybody off the top of their head know what the annihilator of 4x would be?
D squared.
D squared, right? You just take 2 derivatives of 4x and it becomes 0. So remember, the idea here is how can I turn my expression into 0 by using derivatives? So when you have 4x, remember the 4 doesn't matter. And the derivative of x, if you do it twice, it'll become 0. So this is going to be a d squared for this first part. Okay. What about, does anybody, this one again, if you would have this in your table, the 9 does not matter. Does anybody know what the annihilator of x times e to the 2x would be?
D minus 2.
There would be a d minus 2 because that's the annihilator of e to the 2x. But the fact that there's an x in front of it, if you look in the table, this is going to be squared.
Sweet.
Okay. Now, very important question. What do I do with these 2 individual annihilators for those two? So this 4x was the annihilator going with d squared, and d minus 2 squared is the annihilator going with 9x e to the 2x. What do we do with those 2? Multiply them, right? Even though there's a plus here, down here we multiply them. That was something you were supposed to pick up in that video, right? In the video last weekend, I very much emphasized that. Okay, so there you go. That's your annihilator. And so your new roots your new roots are coming from that, right? The new roots will be 0, 0, 2, and 2. Okay, so I'm just looking here. Without rewriting the D's as R's, I'm just kind of directly saying, look, the roots are going to be 0 and 0 and 2 and 2. So we jot them down here. And now I'm going to try to write down the form of the particular solution. So I'm ready for some more volunteers. Anybody who hasn't had a chance to jump in yet, want to help me here? Actually, James, maybe you want to do it.
C6?
Yeah, C6. Can I call it A?
Yes.
I like to switch to different letters, as you know, just so I don't confuse these letters with the first ones. Yeah, so the root being 0, e to the 0 is just 1, and so we have an A in front of that. Okay. Can I get another volunteer for the next term? Bx, awesome. We're stacking an x because of the repeated root. Okay, can I get another volunteer for the next term?
C cubed e to the 2x squared,
C times what?
x cubed
X cubed,
to the e to the 2x.
e to the 2x. Why is it x cubed here?
We already had them deal with the 2.
Okay, these new roots, you have to be careful. They might be repeating roots that you saw already in step 1, and you have to continue stacking x's. So we left off on C5 x squared, e to the 2x. So now over here, we pick up with the very next power of x, which would be x cubed. Okay, and I need one more term. Somebody want to help me?
Yes.
Dx to the 4th, e to the 2x. Awesome. And that d is not the same d as we use for the derivative operator. You guys know that. So we don't have to worry too much. This is it. And thank goodness, since we have only 2 minutes left, thank goodness we don't have to take 5 derivatives of this and solve for A, B, C, and D. That's going to be good enough. That's the form. And so finally, the last step, y of x equals yc of x plus yp of x. That's the whole story of that problem. What do you guys think? Any questions on that one? Okay, oh my gosh, this is a historic week. I let you go 4 minutes early on Tuesday. I'm gonna let you go 2 more minutes early today. You guys are really gonna be complaining to the administration. Anyway, yeah, I don't have anything else for now. If you do have more questions, I'll be in my office after 8 o'clock tonight. Feel free to stop by. Have a great rest of your day, guys. Thanks for coming.
See you next week.